Good day, first years. This lecture is a continuation of the discussion on crystalline structures from Module 3.1. We will talk about the different kinds of crystal unit cells formed by different metals and their characteristics. In this lecture, you will be able to define the three simple cubic crystalline structures and identify their characteristics as well as calculate the theoretical densities. You have learned in Module 3.1 the different types of crystalline solids, but what makes up a crystalline structure? A crystalline lattice is the regular arrangement of atoms in a crystalline solid. The crystalline lattice is made up of a regular repeating pattern called the unit cell. For example, in the given 3D crystal lattice, the highlighted cube is what we call the unit cell. This is the smallest divisible unit that, when repeated in 3 dimensions, forms the crystal lattice. The lattice points represent the spaces occupied by atoms, molecules, or ions. Crystals are classified using the 7 crystal systems, which is based on their atomic crystalline lattice. The shape of the lattice determines not only the crystal system it belongs to, but also its other physical properties and appearance. The 7 crystal systems are cubic, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, and trigonal. However, in this module, we will only focus on the simplest of the 7 structures, which is the cubic system, or what is also known as the isometric system. This is so called because, as you are all familiar with the geometry of a cube, all 3 axes are of equal length and intersect at right angles. The cubic unit cell is the smallest repeating unit when all internal angles are 90 degrees and all lengths are equal. There are 3 kinds of cubic unit cell depending on the packing of atoms. First, we have the simple cubic unit cell composed of 8 atoms occupying each corner of the cube. Each corner atom is shared by 8 neighboring cells. Second, we have the body-centered cubic or BCC unit cell. Besides the 8 corner atoms, this cell also has an additional atom in the center of the cube. And finally, we have the face-centered cubic or FCC unit cell. This cell also has the 8 corner atoms and an additional of 6 face atoms shared between 2 adjacent unit cells. Now let's talk about lattice contribution of each kind of atom in a cubic unit cell, since this will be important in the next parts of the lecture. First, the corner atom. As I have mentioned earlier, a corner atom is shared by 8 neighboring unit cells as shown in this figure. Therefore, in one unit cell, the contribution of one corner atom is just 1/8 of an atom. Next is the body atom. Since the body atom occupies just one unit cell and is not shared by any other neighboring cell, its lattice contribution is 1 whole atom. And for the face atom, it is shared by 2 adjacent unit cells as illustrated in this figure. Thus, its lattice contribution is half of an atom. Knowing the structure of a crystalline solid will already tell you several properties unique to that particular crystal lattice. In this lecture, we will study different characteristics of a crystal structure, such as its coordination number. This is the number of atoms that touch or are adjacent to a particular atom. Second, we have the number of atoms in a specific cubic unit cell. This is based on the total contribution of the atoms composing one unit cell. Third, a crystal structure also has a particular ratio between the radius of the atoms composing it and the edge length of the cubic unit cell. Take note that we are only discussing crystal lattices composed of a single element, therefore the atomic radius of all the atoms in the lattice is the same. Finally, the atomic packing factor or APF. This is the fraction of space that is occupied by atoms with the assumption that atoms are hard spheres. This parameter describes how closely packed the atoms are in the crystal lattice. It is given by the equation volume of atoms in a unit cell divided by volume of the unit cell times 100%. Now, let us discuss the 3 cubic unit cells and their respective characteristics. First, the simple cubic structure. This is a very inefficient arrangement because of its low packing density, which means it has a lot of empty spaces. Since the general tendency of atoms is to crystallize as closely packed as possible, this ineffective arrangement is rarely seen in nature. In fact, only radioactive polonium is the only known example for this cubic structure. To find the coordination number of the simple cubic unit cell, let us look at this crystal lattice. If we focus on the red atom at the center, we can see that this atom is touching 6 other atoms in the lattice, particularly 4 on the same level, 1 on top, and another one below it. This means that the coordination number for simple cubic unit structure is 6. Take note that the coordination number throughout this lattice is the same. This means that whichever atom you consider, that atom is adjacent to 6 other atoms. We know that a simple cubic unit cell is composed of 8 corner atoms. We also know from our discussion on lattice contributions that a corner atom in one unit cell is just 1/8 of an atom. Therefore, in one simple cubic unit cell, we have a total of 1 atom which we obtain from 8 1/8ths of an atom. Next, let's discuss the relationship of edge length and atomic radius. First, let us define the variables that we will be using. The edge length, which is the length of the side of the cube, is represented by the small letter a. The atomic radius is represented by r. To get the relationship of edge length and radius, take note that for a simple cubic unit cell, the edge of the cube is equal to 2 lengths of the atomic radius. Therefore, the relationship of r and a can be expressed as r is equal to 1/2 a. Then, for the last characteristic of the crystal structure, let's discuss the APF. Recall that APF gives the percent of space that is occupied by atoms and is given by this equation. Since we are assuming that atoms are spherical in shape, the volume of one atom can be calculated using the volume formula of a sphere, which is 4/3 pi r cubed, where r is the atomic radius. On the other hand, the volume of the cubic unit cell is obtained using the volume formula of a cube, which is a cubed, where a is the edge length. To get the total volume of atoms in a unit cell, we just simply multiply the number of atoms per unit cell and the volume of one atom. Thus, the equation of APF can be expressed as the number of atom times 4/3 pi r cubed divided by a cubed times 100%. For a simple cubic unit cell, the APF equation becomes this. The number of atoms in a simple cubic unit cell is 1. The volume of an atom is 4/3 pi r cubed, but we know that the radius is also equal to 1/2 a. So we substitute that in the equation. The volume of the unit cell is a cubed. You will see that a cubed will cancel in this equation, leaving just the constants, which can be calculated to get the APF for simple cubic unit cell as 52%. This means that for simple cubic structure, only 52% of the lattice space is occupied by atoms, while the remaining 48% is just empty space. Next is the BCC unit cell. In this arrangement, atoms are in contact with each other along the cube diagonal and not the cube edge, just like in the simple cubic unit cell. To get the coordination number of the BCC unit cell, let's focus on the body atom. The body atom is touching the 8 corner atoms, which makes the coordination number equal to 8. Take note that the central body atom is not in contact with the other body atoms of adjacent cells. Remember, the coordination number for a specific unit cell is constant. This means that whether you are looking at the body atom or the corner atoms, the number of adjacent atoms is still 8. The number of atoms in one BCC unit cell is 2, which is composed of one whole body atom and 8 1/8 of corner atoms. Next, we know that atoms in a BCC are touching along the body diagonal of a cube as shown by this line. To relate the radius and edge length, we can form a right triangle with the body diagonal, cube edge, and face diagonal. However, we still have to determine the length of the face diagonal, and we can do that by considering the right triangle formed by two cube edges and a face diagonal as shown. The length of the face diagonal is obtained using Pythagorean theorem, that is c squared is equal to a squared plus b squared, where c is the length of the hypotenuse and a and b are the legs of the triangle. Since the edge length is the same for both legs of the triangle, the equation becomes c squared is equal to 2a squared. Therefore, the length of the face diagonal c is a square root of 2. Now, considering the right triangle formed by the body diagonal, it can be seen that the sides of this triangle is as follows. The hypotenuse lies along the body diagonal where the body atom is in contact with two corner atoms. Thus, the length is equal to 4r. One leg is equal to cube edge A, and the other is the face diagonal length a square root of 2, which we have previously obtained. Applying Pythagorean theorem on this triangle, we can get the relationship of r and a, which is r is equal to square root of 3 over 4 times a. For the atomic packing factor of BCC unit cell, we know that this unit cell has a total of 2 atoms per cell and that r is equal to the square root of 3 over 4 times a. Substituting those information in the APF equation and cancelling a cube, we calculate the APF of BCC unit cell as 68%. This shows that BCC is more closely packed and denser than the simple cubic unit cell. Lastly, for the FCC unit cell, the atoms are in contact along the face diagonal. The coordination number for this unit cell is 12. If we focus on one corner atom, we can see that it is in contact with 4 face atoms within the same plane, 4 face atoms on the plane above it, and 4 more face atoms on the plane below. To get the number of atoms in an FCC unit cell, recall that a face atom contributes 1/2 atom in a unit cell per face. Since a cube has 6 faces, that contributes 3 atoms, plus 1 atom formed by the 8 1/8 from the corner atoms. Therefore, the total number of atoms in one FCC unit cell is 4 atoms. To get the relationship of radius and edge length, we will apply the concept we previously used in the BCC unit cell. Since the atoms touch each other along the face diagonal, we will consider the right triangle formed by the face diagonals and the 2 cube edges. Applying Pythagorean theorem, we get r is equal to the square root of 2 over 4 times a. For the APF, we know that FCC unit cell is composed of 4 atoms and that r is equal to square root of 2 over 4 times a. Substituting those in the APF equation and cancelling a cube, we get APF is equal to 74%. This shows that FCC is the most compact and most dense arrangement among the 3 cubic unit cell structures. This table summarizes the different characteristics that we have discussed for each cubic unit cell. It is worth remembering these characteristics since this will be useful in the final part of our lecture, which is about theoretical density. The theoretical density of a crystalline lattice is the same as the density of the unit cell that it is made from. So if you know the density of the unit cell, then you have also determined the density of the crystal itself. The density of a unit cell is defined as the mass of atoms in a unit cell divided by the volume of the unit cell. The mass of the atoms can be calculated by multiplying the number of atoms in one unit cell by the atomic weight of the atom and dividing it by Avogadro's number. Observing the units of the parameters in the equation, this will ultimately give us a unit of grams. If we divide this equation by the volume of a unit cell, we will get the equation for theoretical density, that is, number of atoms n times atomic weight A in grams per mole divided by the volume of the cubic unit cell V sub C times Avogadro's number 6.022 times 10 to the 23 atoms per mole. Remember that the volume of the cubic unit cell is calculated using the formula A cube. Note that the unit of density is grams per cubic centimeter. The volume of one unit cell is very small that it may be given in units of nanometer nm or picometer pm. Therefore, it is also important to know these conversion factors because you need to convert nanometer or picometer to centimeters when calculating the density. The theoretical densities of solid materials depend on the packing or the arrangement of atoms that forms the structure. This graph on the right shows the comparison of the densities of metals, ceramics, polymers, and composite materials. Metals generally have high densities because of the closely packed formation of its particles and that it is composed of heavy atoms. Ceramics are arranged in a less compact formation as compared with the metals. It is also usually formed by elements that are lighter than metals such as carbon, nitrogen, and silicon, among others. Polymers, which is the least dense of the three solid materials, are usually amorphous, which results to its low packing density. These are also formed by light elements like carbon, hydrogen, and oxygen. Composites are materials that are a combination of two or more materials with different physical and chemical properties. Its density depends on the type of materials used for synthesis. Now let us consider this example. Molybdenum has an atomic radius of 0.145 nanometers. The volume of its cubic unit cell is 0.0375 cubic nanometers. What is the geometry of the molybdenum unit cell? The givens in this problem are the atomic radius of molybdenum, which is 0.145 nanometers, and the volume of the cubic unit cell, which is 0.0375 cubic nanometer. To determine the type of cubic unit cell formed by molybdenum, we can use the information we know about the relationship of atomic radius and edge length. To do that, we need to calculate the edge length first. This is obtained by getting the cube root of the unit cell volume. So calculating this, we will get 0.335 nanometers. Next, we will get the ratio of radius and edge length. So 0.145 nanometer divided by 0.335 nanometer gives us 0.433. So from our discussion of the different characteristics of each cubic unit cell, we were able to establish the relationship of radius and edge length for each unit cell. We will then compare the value that we got for the ratio and see which structure shows the same or closest ratio of R and A. As seen in this table, the ratio we got is closest to the R over A ratio of a BCC unit cell. Therefore, the geometry of molybdenum is BCC. For the next example, copper had the most essential industrial applications of the three coinage metals. It has an atomic radius of 127.81 picometer and adopts the FCC crystal structure. What is the theoretical density of copper in grams per cubic centimeters? The givens for this problem are the atomic radius of copper and that the atoms form a face-centered cubic unit cell structure. The problem requires the theoretical density of copper given in grams per cubic centimeters. To calculate density, we will use this equation. The parameters needed to calculate the density are already given except for the volume of the unit cell. This can be determined using the formula A cube. So the first step we need to do is to calculate the edge length from the given radius. In an FCC unit cell, the relationship of A and R is 4R over square root of 2. So substituting the value of the radius, we will get the edge length equal to 361.5013 picometer. Since the required unit is grams per cubic centimeter, units of length must be converted to centimeters. To convert picometer to centimeter, we will use this conversion factor. The edge length then becomes 3.615 times 10 to the negative 8 centimeters. Finally, we will calculate the theoretical density. Substituting the information we know in our equation for theoretical density, we will get this. We know that the number of atoms in an FCC unit cell is 4. The atomic weight of copper is given as 63.55 grams per mole. The unit cell volume is equal to the cube of the edge length, and Avogadro's number is 6.022 times 10 to the 23 atoms per mole. Canceling the units will leave grams per cubic centimeters. Calculating, we get a theoretical density of 8.94 grams per cubic centimeters. If you search for the actual density of copper, it is equal to 8.96 grams per cubic centimeter, which is fairly close to what we have calculated. This ends lecture 3.2, Crystalline Structures. In the next lecture, you will learn all about the types and properties of another solid material, which is polymer. Should you have questions regarding the topics discussed, feel free to contact your respective instructor. Thank you for listening and have a great day.